Okay, that sounds great. So I would like to welcome everybody on this very first session on our Solar Geoengineering Virtual Symposium. And my name is Simone Tilmes, if you don't know me, and with me is Matthew Hendry, and we're both organizing these lectures. This is the first time. We'll may mention it at the end again. We're planning to have the symposia once a month. You saw the invites. Please share if you know people that want to also be part of the email list, and then we'll send out invitations. So yeah, we hope that we can get everybody or somebody who is doing research currently, has a recent paper out on the topics, and this is really a large topic on solar geoengineering or climate intervention that is going from anything you can is connected to it at this point. So if you are interested to present anything, please go ahead and send us an email. That would be great. We may approach some people for the first few times, but I think we have a lot of research we all want to catch up on and know. So, and with no further delay, I think we'll start with our first speaker, which will be Libby Barnes, and she is from Colorado State University. And her focus is on climate variability, climate change, data analysis, and the tools to understand them. She's also very much interested in predictability, jet stream dynamics, Arctic mid-latitude connections, subseasonal forecast predictions, and also machine learning and other methods to understand the statistics of climate change. And so today she will talk about detecting a stratospheric aerosol injection world with explainable artificial intelligence. So Libby, please go ahead and start. Please, we have 20 minutes. And we may, if you want, we can remind you after 5 minutes before the end. So I
think I'll be okay, Simone. I have to teach in not too long, so I have other reasons to be on time today. And thank you for explaining all my acronyms in my title. That was great. Okay, so thank you everybody for coming and listening to this talk. I'm here to really present a range of work being done by many people here at CSU. I'll tell you about that in a minute. Specifically focusing on our work and our approach with explainable AI or artificial intelligence. So I think both myself and the other speaker, Alice, have this figure. So today we're going to be talking about solar climate intervention, which many people I think on the call are familiar with. So that, the process of deliberately increasing the reflection of sunlight from the atmosphere. There are many types of solar climate intervention. And today we're just going to focus on one particular type. So my focus here is specifically on stratospheric aerosol injections. So what's drawn here in the pink box, although of course there are others. And at the end, if I have time, I can talk about how possibly these tools could be used for detecting the impacts and effects of other flavors. So a lot of this work that I'm going to talk about today has been funded and is being funded by a DARPA project that is led by Jim Hurl here at CSU, that I am also co-PI on. And this was really an AI call about climate tipping points, and our focus here was on SAI impacts and the possibility of how it could impact tipping points using AI. So the general idea of this project is goal one was to detect and attribute SAI, or in this case, climate intervention deployment. Two was to quantify Earth system changes and impacts from this deployment. And the third part, which is really exciting and interesting, but I'm not going to be touching on today, is scenario design and simulation, focusing both on these collective actor simulations where the world comes together with an agreed upon set of global targets versus unilateral actors or single actors going out and doing this on their own. And that's another big part of this work that I'm not talking about today. I do like to show a bunch of faces just to remind everyone I'm merely a sort of a spokesperson here. This is our team made up of faculty at various universities, colleagues at NCAR, research scientists, and graduate students all working on these topics. So at this point, there are quite a few simulations, especially in the last year, coming out on these sort of global actor stratospheric aerosol injection deployment. Today, I'm going to focus on our work using GLENS and ARISE. So GLENS, which Simone led, being the Geoengineering Large Ensemble Project, and ARISE being more recent. And they differ in many ways, what model they use, what the background climate change scenario is. For example, GLENS starts in 2020 under RCP 8.5, whereas ARISE starts in 2035 under SSP 4.5. So these are different sets of simulations. However, we've been applying our methods to both depending on the particular situation, how much data we need, et cetera. They have different number of ensemble members. And that comes into being important when you start applying machine learning, which is a data hungry technique. So with that said, we have these different simulations with their different background, no SAI worlds. That is the red line and the orange line. And then, of course, we have the SAI worlds, where on top of that, SAI has been deployed using, it's been applied to keep certain temperature targets fixed using a controller. And that's the green line and the purple line here. The question is, can we detect an SAI world? Once it's deployed, when can we see that it's been happening in terms of impacts on the ground? So this is a nice figure. You've seen many of these if you study climate variability. And the idea here is looking at, or asking the question, can we detect an SAI world? So this is data from GLENS, the first decade after deployment of GLENS, and looking at near surface temperature trends. Now in the red box here is the ensemble average over all 20 ensemble members. And what you can see is after deployment, the first decade of trends are in the ensemble mean are practically zero, they're white. Which means in this case, in the simulation, this is the goal. The goal is to stabilize temperatures at these levels. However, if you look at each member individually, they're not all white. You have positive trends in some regions, you have cooling in other regions, and really most of these colors, as we can see, are from natural variability of the system. That is the fact that the weather and climate variability is still occurring even though we're doing SAI. So the issue here is we're not going to live in the ensemble mean. We're not going to live in that red box. We're going to live in one of these 20 boxes. And the question is, when would we be able to truly say we see impacts or effects of this SAI, especially regionally, I will point out. Globally, when we did take, say, a global mean surface temperature, that's pretty straightforward often to detect. But how about regionally? When can we see that this is having impacts? So today, just to show you one example, we're going to focus on extreme precipitation. So this is under GLENS. This is that, in this case, global mean extreme precipitation metric. The red is the world without SAI, so this is RCP 8.5, and the blue is GLENS. So again, we see that this particular variable is also stabilized after 2020 when that deployment occurs, while as without SAI, this extreme precipitation keeps going up. So if I were to say, just looking at this, when can you detect SAI? You might do some sort of when the red wiggles are outside of the blue wiggles, right? And if we wanted to, we could do some sort of linear trend statistics and some sort of standard error on the trend. However, this is a global mean perspective. And again, what does this mean more regionally? Can we detect what's going on and when these diverge? So we're going to use neural networks to do this. Specifically, we're going to train a neural network to detect SAI from maps of precipitation extremes. We're going to focus here over land. So what does this mean? What we're going to do is we're going to train a neural network, which is just a set, in essence, of regression problems that then get pushed through a nonlinear activation function at the end of just doing a sum of weights. We're going to take a map, any single map from any single year within these simulations of extreme precipitation, and ask the network, did this come from the GLENS SAI simulation, or did this come from the control or the RCP 8.5 simulation? So that's the question we're asking the network. Put another way, we're saying, what's the probability that this particular map of precip came from an SAI world? So the network's task is to distinguish when I give it a map of precipitation from the SAI world and when I give it a map of precipitation from the no SAI world. I can't see almost anybody's videos, so I'm going to Hope that makes sense, and we'll keep going. All right, so this is the task. And I'm happy to talk about the neural network architecture. It's quite simple in this case. Okay, so first, just to make a point, I just want to show you what the task that we're giving this network is. So the top map is the map from 2030 from member number 1 of the no SAI world. And the bottom is a single map from member number 1 of 2030 in an SAI world. Now by eye, if you look at these, to me, it's pretty hard to see much of a difference. And you can also argue that's my color bar. Fine, we can talk about that later. But this is in essence what we're asking the network to do. We're asking it to be able to tell which is which, but over many different years, over many different ensemble members. Once we do this, we're going to use the explainable part of explainable AI, also known as XAI, to better understand how the network was able to distinguish these two different worlds. That is, once we get our prediction, we're going to use that information and propagate it back through the network to ultimately create a heat map that's going to help us know what regions of the globe were useful in making this prediction. And in this way, hopefully, we can learn about patterns of detectable effects of SAI. I will note I have a whole different talk on explainable AI for climate science. And I just want to point out that these explainability techniques are useful for lots of different things. They're useful for those people, well, for all of us, should be skeptical of AI, if for no other reason, garbage in, garbage out. And these can really help you gauge trust that the network is learning what you think it should, or that is scientifically sound. You can use these tools to fine tune and optimize your machine learning techniques. I'm not going to go into that here. And then finally, and this is where this work really falls, is learning new science, actually trying to learn what the network learned so we can better understand the climate system and its response. All right, so I've set up the problem. The network's going to predict which world each map is from, and then we're going to try to understand how it came to its conclusion. So how did the network do? So the results are here, shown here. The darker the color, the more the network got right for that year. So this is testing data. These are ensemble members the network had never seen after it had been trained. We push those maps through. And once the colors get dark, that means the network has near perfect accuracy. So in reading this plot, the network has above a 97% accuracy following, in the years following, after about 2035 or so. Put another way, within 15 years of deployment, this neural network can distinguish which extreme precipitation maps are coming from an SAI world and which are coming from a non-SAI world. Now that the network can do this, our next question is, how is it doing this? Where is it looking? Where is extreme precipitation a detectable pattern, or showing a detectable pattern? And this is when we can use XAI methods to propagate that information back to the network and create a heat map that looks something like this, showing the regions that contributed to its prediction. So you can focus here on the green dots, and these are the regions of the globe that the network uses to know which world we're living in. Now, these are combinations of signal to noise ratios, so high signal, low noise. These are the network's able to take regional information and take advantage of that, and this is where it's looking. Now, it's helpful to compare this to a standard signal to noise ratio, which we're very familiar with as climate scientists. And we do certainly see some similarities, especially over, say, Central Africa, where the signal to noise ratio is high, and the network's also looking in that region. But you will also notice there are other regions of the globe where it's more than just this basic, simple signal to noise that the network is utilizing. All right, so this is looking at global land extreme precipitation, but what about more regionally if we focus in? This is where Zach Laib's work, a former postdoc of this group, has really been focusing. So what about these regional responses? Now his work is using ARISE. The work I just showed you was Glenn's, but now we're going to transition here to ARISE. And in a similar way, he's looking regionally. In this case, we're just showing results for the Northern Hemisphere and the Southern Hemisphere. These are the two different rows for temperature and precipitation. And once again, once those colors get dark, this shows that the network is starting to be quite accurate in knowing which map is from which simulation. Temperature, as you can see, very quickly after deployment in 2035, especially in the Northern Hemisphere, the network is able to know which world we are from. But if you look, for example, at precipitation in the southern hemisphere, so the bottom right, it's harder for the network to know which world we're giving it until much later into the simulation. Once again, though, in the same way, we can use these XAI maps and ask, where is the network looking? So in this case, I'm showing results of ZACs from looking at surface temperature over land. So the left-hand side is the regions of the globe that the network is focusing on to know whether we're in an SAI world or not. And on the right, again, is a standard signal to noise map. And as I made the point before, you can see certainly similarities, but they're not identical. So in many ways, you can, at least as a base, understand how our regression problem, our nonlinear regression, is using the signal to noise as well as other pieces of information in terms of regionality to make its decision. Okay, so Zach did a similar problem, you know, which simulation are we from? But then he went further and he said, okay, let's ask a different question. If we know we're in an SAI world, can we task the network to determine when did it begin? Put another way, if we input a map of, say, precipitation or near surface temperature, can the network tell us how many years it has been since injection? And again, you might say, well, I know how many years since injection. If this is a rise, it was injected in 2035, and I can look at my netcdf file and tell you what year it is. Like, why is this a question? We're not doing this prediction problem for the prediction. Once again, we're using it to try and better understand how the network performs and how it comes to the conclusion that it did. Again, to try and learn some new science. So again, Zach's work is really focused regionally. So here's the result of if it's an SAI world, when did it begin? So the x-axis here is the actual year, and the y-axis is the network's prediction of the years since injection, or the truth. So the black line is the truth. A perfect prediction would be that black line, and the green line is how the network did. And you can see in some cases, for example, in Antarctica, it's quite poor. It's really bad. In essence, meaning that the network is not finding the signals that it can use to determine how many years since injection. But other regions like the tropics or the Amazon or Southeast Asia, the network is able to determine how many years it has been. What this implies is there are impacts, if you will, potentially there are impacts of SAI or differences between an SAI world and a non-SAI world that evolve with time, and that the network is able to learn these. Okay, so the last example I want to go through is work by research scientists in our group, Dr. Antonios Mamalakis. This is new work that he's just hopefully going to submit in the next few weeks. This is about distinguishing the climate under an SAI world and the reference climate, or the climate prior to deployment. So the question he's asking is, how distinguishable will the SAI climate be from a pre-deployment climate? Again, we're focusing here on a rise. So how distinguishable are these climates? His reference climate here is shown in the pink box, and the blue box is our definition of our SAI climate, so our future climate. And the question is, how distinguishable are they, again, by our machine learning technique or our data analysis technique? Where are they distinguishable? And can we come up with a framework that we can use this approach to apply to many different climate variables? All right, so how do we do this, or how does Antonios do this? Well, he sets this up once again as a neural network prediction task. So he's going to input a map from a certain year, from any particular year, from a simulation from either the ARISE SAI run or the no SAI, so the SSP4-5 run. He pushes it through this neural network, and he tasks the network to predict the probability that the map originated from the SAI climate. That is that, if I go back for a minute, from the blue box. So did it come, we're tasking the network to tell us, did it come from the blue period or the pink period? Once the network makes that prediction, we can then once again go back and ask, how did it come to its conclusion, and better try to understand the regions of the globe that were most important. Now, one of the things that's really interesting about how Antonios has set this up is the higher the network's accuracy, that the better the network is at doing this task, the higher the degree of distinguishability between that pink and that blue box. So our idea here is if the network is very good at distinguishing these two climates, it means there's something different about that. If the network is having a hard time distinguishing between these two climates or these two climate variables and states, then it implies that the network, those two states are less distinguishable, at least from this neural network's perspective. Okay, so the final plot has a lot of information, but he has done this for many different climate variables, because of course, when we say how distinguishable is the climate, everybody's interested in something else. You might be interested in precipitation, drought, temperature, pH, Arctic ice. So how do we read this? So along the x-axis, I'm not going to go through all of them, don't worry, but along the x-axis is many different variables. And on the y-axis is the network's ability to distinguish between these climates. Now, the blue dots show you the case that I just explained. Can the network distinguish between an SAI world and the reference period? And you can see that when the blue dots are large, so near 100%, that means that the network is able to distinguish between these two periods. The pink dots, what I didn't mention, was doing the exact same thing, but distinguishing between that pre-2035 period and the post-2035 period, but under SSP 245. So that is, climate change itself alone without SAI is already causing our climate to change and be distinguishable from one period to the other. And so going through here, you can see that when the pink dots are larger than the blue dots, that is when the network has an easier time distinguishing pure climate change periods from an SAI world and a reference period. This suggests that SAI in these simulations is decelerating distinguishable changes in our climate. In fact, for certain variables like precipitation over land, SAI actually largely preserves the pre-deployment precipitation extremes because the network is unable to distinguish an SAI world from the reference climate. And finally, you'll notice one thing that we used when we were doing this work to make sure it made some sense is the very far right is ocean pH. This is something we know that SAI, it's not changing CO2 concentrations. In fact, CO2 is still rising in SSP 4.5. And so we know that if you feed the network maps of pH in the ocean, it should certainly still be able to distinguish whether we're pre or post deployment of SAI. And indeed, the network has near perfect accuracy, no matter what situation you're looking at, which is consistent with the fact that SAI is not a solution and certainly does not fix the pH problem. All right, so my conclusions here. First, I'm going to argue that XAI techniques, they offer a different way than maybe sometimes we do, analyzing and assessing SAI impacts. I think it's critical to have these well-designed climate model simulations. That's the only way we got this to work. And in using this approach with these beautiful simulations, we have the potential to reveal patterns that maybe are harder to find with just linear methods. And finally, some of our results suggest that regional impacts may be more quickly detected than some previously thought. Okay, thank you.
Thank you very much. Clap. Very nice talk, very good. So our meetings here have sufficient time for discussion, hopefully, maybe not sufficient, but some time for discussion. We scheduled about 10 minutes. I'm not sure if there are questions now, please raise your hand. You can also put questions in the chat. And since we have started a little late, we may go to I think 8:35, and then we'll go right to the next talk. So we're not going to go over. Okay,
Hey, Simone, I might need to go at like 8:31, if that's okay.
Okay, 8:31, yes. Perfect. So quickly, first is Katie. Please go ahead and mute yourself.
Yeah, thanks, Libby. Great talk. Really nice summary of your work. I'm curious about the XAI heat maps and whether you could make sense of some of the regions that were popping up. I think for example, I noticed Southern South America popped up in 2 of the examples. So have you been able to draw any conclusions about why certain regions are coming out as in those sort of techniques?
Yeah, so a bit. So in some of the earlier work that I showed you, it's large, like the signal to noise, I can't remember in that exact region, the signal to noise does nicely align in a lot of cases with what we're seeing. In South America, I don't know yet although Antonius has been looking at, especially he's been looking at more northern South America. So I guess I'm going to answer, I don't know yet, Katie. I don't, but the first step was finding these regions, and now we can go and look more scientifically at why is it figuring this out. One thing I like to point out is the signal to noise, as you know, is a big part of what the network is doing. It's looking for the signal, and there's lots of climate variability and noise, and especially across ensemble members, but it's also using regional information that maybe go together or go against each other. And this is something we're trying to figure out, is how do we then use these heat maps to determine when one region is important because another region was important too. And we don't have an answer for that part yet.
Yeah, thanks. I mean, Southern South America is one of the only bits of land at that latitude. So I wonder if that could be why.
It's all it's got. Yeah, it's sort of all it has. Yeah, maybe. And I didn't show you, but Antonius has been using these heat maps and trying to understand how they differ across these two different periods as well. But that's a whole different, that's another plot. So hopefully that will shed some light too.
Okay, great. So now Valentina has her hand up.
Hi. Maybe you don't have time to answer, but the question would be about if actually a different strategy was deployed from the one that is using Horizon Glance, what do you think of what you presented could be applied to a different strategies? Like, could we still look at this region to identify if SAI had been deployed or not, or would it be really dependent on the strategy?
It will be incredibly dependent on the strategy. So our goal in our group is to come up with methods that would apply across all of these strategies, but the actual results or answers will certainly be different. No question. Just like we know that how dependent the climate impacts are based on strategy alone, in the same way, these regions will likely be impacted too. So we're trying to, I would actually argue that these works are trying to argue that this is a method others can use as well, depending on what they're looking at, rather than here's the answer, everybody, this is all you need. That's not what we're trying to do. So think of Glens and Arise in these cases as merely test cases or the sandbox within which we are trying to use these tools and perfect them.
Maybe you should train a neural network on different strategies to figure out.
There you go. Figure out which, yes. And actually there is a computer science paper thinking about using a neural network to try to find the optimal strategy. But they came to the conclusion that the climate system is complicated, so they were going to simplify it into a 1D column model and then do all their testing that way. So I think there's room for improvement.
Do we have
I have time for one more? Yeah,
one
sure.
more. Okay, Hongwei, please go ahead and ask your question.
Very nice talk. So I'm wondering about the figure you shows using machine learning to predict the SAI year, like how many years we deploy SAI. In that one-to-one figure, seems like the machine learning method cannot predict the very early years or the very end years. I'm just wondering, do you have any comments on why that caused what caused that? Like
Yeah, so you're talking about the slope, right, of that line.
Yeah. The slope is smaller for the machine learning method.
Yeah. So I mean, I have some thoughts. First of all, the early years alone makes sense because it's hard to tell maybe even if SAI has been deployed at all, let alone if it's been 1 year or 3 years yet. On top of that, and this is something I know Zach's on the call, but I'll just speak generally. Most regression methods don't like to guess the extreme, the zeros or the big numbers, purely from the fact of how the loss function is created. And so that could also be the network trying to play it safe. And oftentimes when you have these types of tools that are trained on some sort of minimizing the mean squared error, they like to be somewhere in the middle. But that's more of a technical reason.
Maybe a quick follow-up is like, would that slope be related to the early on when you said the heat map of the XAI, like if the signal to noise would
yeah,
be
that could explain the early. Yeah, that could easily explain the early period, but not the late period. The late period is my guess is that just the network saying I don't get enough points to guess such a big value. So one can play with the architecture to try to fix that.
Yeah, makes sense. Thank
potentially. You. Okay, thank you.
Thank you, Libby, once again.
Yep.
Very nice talk, and please stop sharing. So I hand over to Matthew now to share the second half.
Okay, thanks, Simone. So next up we have Alice. Do you want to start sharing your screen? So
Yep.
Alice Wells is a PhD student at the University of Exeter with Jim Hayward. She started doing some climate modeling of volcanic eruptions, and now she's starting to look at deliberate injection of aerosols in the stratosphere. And today she'll talk to us about the different climate impacts of different injection strategies. So go ahead, Alice.
Cool, thanks, Matthew. Can you guys see my screen okay?
Yes.
Cool. So yes, I just want to thank you both for inviting me to talk today. Like you sort of mentioned, I'm going to be sort of talking about the differing climate impacts that we see after implementing 2 different stratospheric aerosol injection strategies into UKSM. I think most people will be familiar, but I'll just go over it in case. So stratospheric aerosol injection is a proposed method of climate intervention or solar radiation modification. Similar to Libby's plot here, we're looking at that top one. So you've also got marine cloud brightening and cirrus cloud thinning, but we're going to be focusing on SAI. And it's a method of sort of trying to reduce the negative impacts on the weather and the climate that we associated with climate change. And we achieve this by increasing the amount of sunlight or solar radiation that we're reflecting by clouds or particles in the atmosphere. And SAI in particular is sort of aiming to mimic the effect we see after a large volcanic eruption. Like Matthew said, that's kind of where I started. And that's sort of when the SO2 is injected into the stratosphere and then it oxidizes, and the sulfate aerosol, which is quite reflective, can then provide a cooling on the global surface temperature. So yeah, today I want to sort of share with you an overview of some of the impacts that we see on both the climate and the stratosphere, but also how important it is what injection strategy we choose on determining the climate impact. Oh, the slide's not changing. There we go. So firstly, I just wanted to briefly talk about the proposed cooling scenario. So what climate are we starting with and what goals are we trying to achieve? So first off, we have this quite scary high tier emission scenario, SSP 585. And this scenario reaches sort of temperatures, I think 7 or 8 degrees above present day across large areas of the Northern Hemisphere by the end of the century. And this is our projected warming scenario in this analysis. And then secondly, we have this sort of medium tier emission scenario, SSP 245. And this has a much more sort of moderate warming by the end of the century against present day in comparison to SSP 585. Although when we look at a rise, this is the baseline. But this is going to be our goal in this analysis after we implement SAI. So as part of the Geoengineering Model into Comparison project, or GeoMIP G6, we have set up 2 experiments which aim to lower the global mean surface temperatures from SSP 585 to SSP 245. Now, the first of these experiments is G6 sulfur. So this is injecting SO2 uniformly between 10 degrees north and 10 degrees south, between 18 and 20 kilometers. And we actually manually adjust the amount of SO2 that's injected every 10 years. So a bit different to Glens and Arise. And those sort of values are based on the temperature target we're trying to achieve. And then our next strategy that we're going to be looking at today is G6 sulfur controller. So this is injecting SO2 at 4 different latitudes, 30 degrees north, 30 degrees south, 15 degrees north, and 15 degrees south, and that's at 21.5 kilometers. And similarly now to Arise and Glens, this strategy changes the injection amounts at each of the 4 locations independently using a feedback controller to meet certain objectives. And I'll go back to those objectives in a bit. So here we are looking at the different rates of injection of SO2 for G6 sulfur. And you can see there that sort of how much it increases every 10 years as like a manual increase. And by the end of the century, we're injecting 21 teragrams of SO2 per year. So that's about a Pinatubo every year. And then when we compare that to G6 sulfur controller, you see that more sort of continuous increase because it's being changed every year. And generally, we sort of see a similar amount of SO2 injected over time, but sort of between 2060 and 2090, we see a bit more in G6 sulfur. And at the end of the century, see a little bit more in G6 sulfur controller, but roughly they're about the same. So the difference with the feedback controller is that it determines not only how much SO2 to inject, but where of the 4 latitudes it's injecting, based on some temperature targets that I'll mention in a moment. So in this scenario, we see actually most of our SO2 is being injected into 30 degrees north and 30 degrees south in comparison to quite a little injection in between 15 north and 15 south. So the temperature targets, as per the G6 scenario, both strategies are set up to try and meet the yearly global mean temperature of the SSP 245 scenario. So that's that baseline, the dotted line there. And the SSP 585 warming scenario is in black there, and you can see it's about 3 degrees warmer than our target by the end of the century. So that's kind of to give you an idea of how much cooling we're trying to achieve. And both scenarios actually do a really good job of cooling to that baseline. Now, I mentioned that G6 sulfur controller had some other temperature targets. So they are the interhemispheric temperature gradient and the polar equator temperature gradient. So with the interhemispheric gradient, both injection strategies actually meet this target. That's up on the top here. But we're not actually controlling for that in G6 sulfur. So we kind of get a buy one, get one free. But then with the pole to equator ratio, you can see that actually the G6 sulfur strategy kind of follows the warming scenario there. And what we'll see in a moment is that's due to the fact there's too much tropical cooling relative to the high latitudes. But the G6 sulfur controller does a much better job at sort of maintaining that target until we get to the end of the century there. So where does the aerosol go? Well, we can have a look at the distribution of the stratospheric aerosol optical depth at the end of the century. And you can see why, when looking at this, there might be a bit more tropical cooling relative to high latitudes in the G6 sulfur strategy. And that's because the majority of the aerosol is remains around the equator. There's very little spread to the high latitudes. And when we compare that to the G6 sulfur controller, we can see that actually the aerosol is much more evenly spread, especially throughout the mid latitudes. But again, that's not entirely surprising because we're injecting mostly at 30 degrees north and south. But another way to look at that is to have a look at the zonal stratospheric aerosol optical depth. So we're just averaging across the longitude in that previous plot to see the distribution. And what's interesting is that actually throughout the simulations, the global AOD is very similar in both strategies. So really, the main driver is that difference in the distribution of the aerosol optical depth. And you can see that in the G6 sulfur strategy, most of that is stuck in the tropical pipe. So this sort of shaded region is just where we're injecting, and then the dots are also where we're injecting for the G6 sulfur controller strategy. And some sort of studies have sort of indicated that UKSM is a bit more sensitive to tropical confinement compared to maybe other climate models, but it's also just the nature of an equatorial injection strategy that you have a much more uneven AOD distribution globally than when we inject at perhaps 15 degrees north and south and 30 degrees north and south. So I'm now going to move on to kind of a general overview of some of the climate impacts. We're going to have a look first at the zonal temperature or the zonal evolution of the surface temperatures. And all of these plots are going to be compared against the target SSP 245. And so you can see when we're looking at our warming scenario, obviously everything warms pretty much everywhere, but we also see quite a bit of polar amplification, especially in the Northern Hemisphere. And when we're comparing our two injection strategies, ideal world, this would be white, but obviously it isn't. And so G6 sulfur, we see this classic overcooling of the tropics that we've seen in other studies, and this undercooling of the high latitudes by the end of the century. And that's become quite typical of equatorial injection strategies. And I've just added some stippling here to show where the temperature is outside of the range of variability within SSP 245. So you can see actually that this overcooling and the underwarming is outside of what we would usually expect from our target temperature. Although it is worth noting that we do only have 3 ensemble members. And then when we have a look at the G6 sulfur controller and moving our injection away from the equator, we ameliorate that overcooling in the tropics. We don't see much cooling. If anything, we see a little bit of an overcooling, an undercooling, sorry. But we do still see this undercooling in the poles, but the magnitude is much more reduced in comparison to G6 sulfur. And actually, when we look at that variability, even some in the Northern Hemisphere, is still within the range of SSP 245. So if we have a look at just the last 20 years of the century, we can have a look at some of the regional differences in surface temperatures under the 2 strategies. And I guess we've kind of fairly well established now that we have this overcooling in the tropics. When we look over sort of Central Africa, there's over 1.5 degrees cooler than you see, than you would expect if it was an SSP 245 scenario. And then you see sort of like over Northern Europe, North America, and over Antarctica, you actually have this undercooling. But it is still significantly cooler than SSP 585, which is where we're trying to cool from. And then again, when we move our injection away from the equator, we do reduce that large overcooling over Africa and over India. But interestingly, we see a little bit of undercooling over the Amazon, and we still have that sort of signal in the high latitudes. So we've kind of ameliorated the worst of the impacts, but we still have some regional differences. So if we move on to sort of looking at precipitation and thinking about the hydrological impact, they mostly vary by region, but global mean precipitation is kind of generally expected to increase under climate change. When you've got warmer air, you can retain more moisture. And so it's expected that you have a larger increase in precipitation in our warming scenario as compared to our target scenario. But then when we're changing the top of the atmosphere's relative balance, we see a reduction in global mean precipitation. This has been sort of seen in a few studies, but it's interesting to note that when we inject at the equator, we see this sort of sharp decrease in precipitation around the years that we're seeing that overcooling. And then we see less precipitation in the equatorial strategy compared to G6 sulfur controller. So when we have a look at some of the regional differences, we're going to have a look at the annual mean precipitation minus evaporation, or P minus E, against present day. And P minus E basically measures, or is a useful measure of water availability at the surface. And it can be a bit more relevant for climate impacts assessments over standalone precipitation. So we're going to have a quick look at the global warming scenarios. So we see this kind of drying over the Amazon in both scenarios and sort of moistening of North America and Greenland, but we just sort of see larger magnitudes of this in the SSP 585 scenario. And then we also see in the 585 scenario this moistening over Africa and sort of more so over Eastern Russia and East Asia. So if we want to compare that to our SAI strategies, G6 sulfur maintains this large drying over the Amazon, so that's similar to what we see in the 585 scenario, if not worse actually, because we lose that bit of moistening there. But G6 sulfur controller can offset some of the drying. It's quite difficult to see, but there is a slight reduction in the magnitude of that. If we then have a look at Eastern Russia and Asia, you can kind of see that we have sort of similar patterns, but sort of smaller magnitude potentially. And interestingly, in G6 sulfur, we see some drying over Southeast Asia and Malaysia. which we don't see in G6 sulfur controller or our warming scenario. And then finally, if we have a look at Central and Southern Africa, in G6 sulfur, we kind of see this mixture of drying and moistening, and which is kind of similar spatially to our target, if not in magnitude. And then when we look at our G6 sulfur controller, we see this moistening, which is very similar to the scenario that we're trying to cool from. So essentially, a lot more work needs to go into looking at why these changes occur and looking at far more detailed analysis. But this is just to kind of point out that a lot of these changes to regional precipitation, but also P-E, are really dependent on the location of the aerosol injection, because it can change the intensity of these changes, but also, as we can see here, change the sign. And also just to note that there would be more significant changes in the seasonal impacts, but I'm not going to go into that today just because of time. So we're going to have a quick look at some stratospheric impacts. So if we're looking at the zonal vertical profile of the average temperature at the end of the century, again against our target of SSP 245, we're seeing sort of a very typical picture of a warming scenario, seeing tropospheric warming and then upper stratospheric cooling, which is associated with greenhouse gases increase. And then we've just got this zonal average against our sort of baseline. So we can see again that warming and cooling. When we compare this to our G6 sulfur injection strategy, so injecting at the equator, you know, we're reducing that tropospheric warming, fine, but then we have this massive stratospheric warming. Again, this has been seen before, but just nice to have a look at. And you can see that's, you know, almost 7.5 degrees of warming across this sort of area. And when we then move that away from the equator, we see sort of spatially a similar pattern of warming, just to a much lesser degree of magnitude. When we look in that zonal average, it's reduced almost by half or over half, I think. And again, like I say, this has been sort of seen in some other studies comparing sort of equatorial versus latitudinal. But really the reason we want to have a look at these stratospheric temperatures is because they can have significant impacts on general circulation changes, stratospheric dynamics, and then this can affect things like regional precipitation change. So these results are definitely sort of showing and confirming that the location of the aerosol injection can either have very detrimental impacts on stratospheric heating or ameliorate some of those impacts. Some of the other variables, again, that I would love to show now but haven't got the time, are things like stratospheric water vapor and zonal winds. But I can just show you some stuff we've had a look at with the QBO. So for those that may not be familiar, the QBO is sort of this regular oscillation of the winds above the equator. And every sort of 14 months or so, they change direction. So in sort of red and orange, they're westerly, and the blues are easterlies. And changes, or the QBO, for instance, can affect the Atlantic jet stream, for example, and this can then change the weather conditions over Northern Europe, for example. So it's kind of important to see how that might change under climate change. We can see that the frequency increases. But under the equatorial injection strategy for G6 sulfur, it breaks down completely. We don't really see a cycle by the end of the century, and that's obviously something that we may not want to do. But again, similarly to some of our other plots, when we move that injection away from the equator, we see that the QBO doesn't break down. It might look a little bit different to our target, but there is still a cycle there. So we have ameliorated the worst of those problems. So generally, I think the message should be pretty clear that if we're undertaking equatorial injection strategies to offset, you know, large degrees of warming, we can see some fairly detrimental impacts. You know, where the aerosols get stuck, and then, or especially in UKSM, can cause this overcooling of the tropics, stratospheric warming. But when we move away from the equator, we can ameliorate some of these differences. We can maintain that pole to equator gradient. reduce stratospheric warming. But obviously, that's not to say that there aren't negative changes or impacts. Regionally, we see massive discrepancies in surface temperatures and changes to the hydrological cycle. We still have stratospheric warming and changes to the QBO. So there's lots to investigate and have a look at. But I just want to, if I can, just finish off and say that I've also started to look at some indices of extremes and looking at some more impact-based metrics, but sadly that wasn't quite ready to share with you today. So if anyone has any advice or feedback or any insights that you'd like to share with me, then please do, and I'll finish there for any questions.
Well done, Alice. Thank you. That was great. So if you have any questions, please put your hands up. I think the first one was John. If you want to go ahead, John.
Yeah. What are the relative emissions in those two cases, the sulfur emissions?
So if I just take you back. So these are our total emissions. So this is, I meant to mention actually, this starts in 2020. All the way through to 2100, but yeah, by the end of the century it's around sort of between 20 and 25 teragrams per year of SO2.
Thanks.
No problem.
Simone, you're next.
Yeah, very nice. Thank you so much for all that work. And it's really nice to see how your model from Hedgeham can do this now, can really do the injections like we did in our model in YChem. And that, of course, we have not we have done the Glenn scenario, the Arise scenario, as you know, but we haven't done this particular one, I think, was the 4 injections, because that wasn't the protocol. So is that something that you think would be a good thing as a multi-model comparison? So thinking about, I was very interested to see that you have an increase in rainfall over India in both cases, while we, in some case, see a reduction. That certainly has to do with the shift potentially in rainfall or not that you get from the IDCZ. But, we also had other scenarios, and I think you guys also did other scenarios that we have done more similarly. So maybe the question is, this is one model. What can we learn from a multi-model perspective?
Yeah, I think that would definitely be an interesting perspective, because obviously, so for those that don't know, Matthew's had a look at sort of a rise in comparison to CSM with UKSM, but you're not offsetting quite so much to start with. So obviously it's starting with SSP 245, whereas we're going for SSP 585. So it would be nice to have a look at how other models sort of do that, because there's comparisons with G6 sulfur, but it would be nice to have a look with the controller as well, and seeing if I know in CSM, I think you get more in 15 degrees north and south. Am I right in saying that? So it would be interesting to see if that would be the same case with the larger warming and cooling. Definitely.
Thanks.
Great. And so next was Andrew.
Hi, yeah, I wanted to ask a question that's applicable to a whole bunch of modelling exercises. I don't really understand why people monitor preset rather than more meaningful metrics like soil moisture, which is very important for agriculture, or hydrological drought, which is useful for urban water availability, or extreme preset, which is useful for flooding, because these are metrics that are much more, they're much more applicable and useful.
Yeah, so unfortunately, the data is not quite downloaded, and I'm still waiting on some of that analysis. So that would have been nice to share. It's kind of why I wanted to have a look at P-E rather than just precipitation. But yeah, I'm definitely going to be looking at some of the extremes, because I just think they're quite interesting to look at. And like you say, it would be nice to see things like drought days or extreme rain events. I think that would be really interesting for people to look at. And also, if you're talking to sort of members of the public, it might be a bit more relatable, depending on why you're having those conversations. But yeah, it would be interesting to look at for sure.
Great. And next, Hongwei.
Okay, yeah, very nice talk. I have a question about the QBO slides. So it seems like in one scenario, the QBO is kind of break, and in other we still have it. I'm just wondering, have you checked like gravity waves in those two scenarios to see like why there is a difference?
I haven't actually. Pretty much as far as I went with the QBO was plotting it. But it's definitely something that I know a few members of the group here are wanting to look at. It's not really my area of knowledge, but I think that would be really interesting to look at.
Cool, thank you.
Thanks.
Great, Simone, do you put your hand back up?
Well, just to follow up, we did in CESM, if you're interested, have a similar study, not with the G6 sulfur, but we're looking at the QBO. There's a paper by Jagerrichter as well. So if you are interested in that, there's a GLENS model study on the effects of QBO using a controller, and you see the same effects that the QBO doesn't shut down. And that's mostly when you're outside the tropics where you inject. You don't get the changes that you get when you inject right at the tropical latitudes. And there's already literature to this, so you can also look at that.
Thank you.
Sounds good.
Great. Are there any last questions? If not, let's thank both our speakers again. And it's been great to have you all. Again, if you want to participate in giving a talk, please reach out to either me or Simone, and we'd be very glad to have you in these monthly seminars. And yeah, thank you very much, and hope to see you next month.
Thank you all for coming. See you next month.